Welcome to our summary of Day 2 of the Keystone Symposia on Neuroinflammation in Diseases of the Central Nervous System. Today was the first day of talks, and if the standard of talks today is anything to go by, it's going to be an amazing conference because all of the talks today were phenomenal. I just want to give an overview of 3 talks that we heard today, and I won't go into details of the specifics of the projects that they were working on, but just give you a broad overview of the concepts that they discussed, and hopefully we'll be able to give some more detailed summaries of their research over the coming days and weeks. So the first talk that I want to highlight was by Carla Schatz out of Stanford University, and Carla was talking to us about the concept of brain plasticity. So brain plasticity is essentially the brain's ability to remodel and rework itself based on what it's experiencing at the time. What Carla told us was that this concept of brain plasticity, or this ability to remodel itself, is only possible during specific critical developmental times during our lives. And then once we reach adulthood, we've lost this ability. However, what her group has identified as the molecule that's critically important for the loss of synapses or the loss of this brain plasticity, and what they've been able to show in some mice models, is that if you can knock out this molecule, the mice are able to regain synaptic plasticity or brain plasticity and be able to regain that ability to remodel itself. Now, Carla talked about this in relation to the effect that it may have on Alzheimer's disease. However, the concept of brain plasticity is something that is important and has wide-ranging effects across a range of neurological disorders. So the second talk that I want to talk about was given by Glenn Roll from the Fox Chase Cancer Center. And Glenn was talking to us about the notions of infections being a causative agent in a number of neurological conditions. So what's been known for a while, or what's been implicated for a while, is that infections seem to be associated with a number of neurological conditions. For example, multiple sclerosis is a classic example where Epstein-Barr virus appears to be implicated in the onset of disease. However, as Glenn mentioned, one of the key problems with this notion is that very rarely do you actually find any of the virus or infection at the site or at the lesion where the disease is taking place. The other problem with this is that often the diseases or the infections that are implicated tend to be very ubiquitous or very common in society. So what Glenn discussed today was whether or not it's possible to get an infection somewhere else in your body that then sends an immune response into the central nervous system. And Glenn's group's been able to show this in a really elegant manner by taking mice and infecting them with 2 separate viruses. One virus in the brain and another virus externally, elsewhere in the body. What he showed from doing this is that if you then look at the brain tissue of these mice after they've had this double infection, that while the main infection elsewhere in the body has been dealt with by the sites there, the immune cells specific for that virus also were able to migrate to the site of the other infection in the brain. This is really interesting because this indicates that there may be a possibility for viruses that don't affect in the central nervous system to somehow cause an immune response or an autoimmune response within the central nervous system. So the last talk that I want to talk about today was from Robin Klein, and Robin's based at the Washington University School of Medicine. And Robin was talking to us about the blood-brain barrier and permeability associated with it that's often seen in neurological conditions. More specifically, she was talking to us about certain protective mechanisms that they've identified that helps stop the blood-brain barrier being permeable. Now, Robin talked about it in the context of a viral infection, and her model used West Nile virus. But what they saw was that specific molecules called cytokines, and in particular interferons of the innate immune response that were released in relation to the viral infection caused the blood-brain barrier to close up. Interestingly, what Robin suggested is that there's actually potentially a plan A and a plan B in terms of the blood-brain barrier when it comes to infections, and this is obviously possibly transferable to other autoimmune conditions such as MS, where we know that the blood-brain barrier becomes permeable. So what Robin suggested is that in plan A, we have these molecules that are released that cause the blood-brain barrier to close itself as much as possible. However, if there's a really large amount of virus around, some virus may get through and infiltrate into the brain tissue. And in this case, the blood-brain barrier goes into plan B, which is actually then to open up itself more and become more permeable so that cells of the immune system are able to pass through and start to clear the virus that's got into the brain tissue. And this is really interesting because blood-brain barrier permeability is obviously a crucial factor in a number of different neurological conditions, so being able to understand it better has wide-ranging implications. So we'll be back tomorrow with more highlights, so stay tuned. Again, if you have any questions on anything that we've discussed today, please comment below and we'll get answers to you as quickly as possible.